In the last class, we discussed about the necessary and sufficient condition for an ideal to be maximal and prime in a commutative ring with unity. The results we arrived at are an ideal M in a commutative ring R with unity is maximal if and only if R by M is a field. And the second condition for prime ideal, an ideal N in a commutative ring R with unity is prime if and only if R by N is an integral domain. And we know that every field is an integral domain. So let's find out, is there any relation between maximal and prime ideal? So let M be a maximal ideal in R. R is a commutative ring with unity, which implies R by M is a field. That implies R by M is an integral domain. And that implies M is a prime ideal. So the third result is every maximal ideal in a commutative ring with unity is also So let us do some examples here. Let's take R equal to Z6. 0, 1, 2, 3, 4 and 5. Our objective is to find out the maximal and prime ideals of this. And this is a commutative ring with unity, which means that if we can find a maximal ideal, that's automatically a prime ideal. So our aim is to find a maximal or prime ideal. So it's an ideal. So every ideal is a subring. So every subring is a subgroup. So we will find out the trivial subgroups of this. So the trivial ideals actually candidates for ideals are 0, 3 and 0, 2, 4. And you can easily verify these are subgroups, these are subrings, and these are also ideals. to find out, to verify it's an ideal, what we need to do is multiply every element of Z6 with every element of this ideal or this subring and see to that it's a member of this. Similarly here. So I'm going to leave to you to verify these two are ideals. How do you make sure that this is maximal or prime ideal? We'll take the quotient of this. So our Z6 over 0, 3 will be, actually if you take this as n plus 1, n plus 2. This is actually isomorphic to Z3. And Z3 is a field. That means 0, 3 is maximal and hence it is prime. Because this is a commutative ring with a unity. Similarly, 0, 2, 4 is a maximal ideal and hence it is prime. So these are the two maximal and prime ideals of Z6. Here, in this case, it is isomorphic to, the quotient is going to be isomorphic to Z2, which is also again a field because 2 and 3 are prime numbers. Let's take another example. R is equal to Z2, and this is actually a collection of ordered pairs. And you can find this is a commutative ring with a unity, with a unit as this, multiplicative identity. Again, the ideals are 0, 0 and 0, 1. There are two more ideals, one more ideal, 0, 0 and 1, 0. These are the non-trivial ideals. There are two more ideals here. One is just 0, 0 and the other one is the whole of R. Same case here. These are not the only ideals. There are two more ideals, and that is the trivial ideal, just 0, containing just 0 element, or the whole of R. So again, if you take the quotient, let's take this as n1 and this as n2. So I will write it as this is n2, and this is n1. So R over n1 is equal to n1 comma n1 plus 1. And this is again isomorphic to, this has got 4 elements, this has got 2 elements. So if you take the quotient, you'll have 2 elements here. And this is again isomorphic to Z2. The verification of isomorphism, I'm going to leave it to you. Isomorphism does not mean that it has got the same number of elements. It also should obey the binary operations on both sides. It should preserve the binary operation. So multiplication and addition. Same case here. So this is again a field and implies n1 is maximal and prime, and so is n2. So these are the two maximal and prime ideals of this ring. Now we are going to discuss about the structure of an ideal. Structure of an ideal in f of x, where f is a field. This is a ring even though f is a field. F of x is the collection of all polynomials in x. And we know that this is a ring. So we can think about ideals here. Before we get into the details of the structure of this particular kind of ideals, let's recall some of the results in the ring of polynomials. The first one is division algorithm. Division algorithm says like this: let f of x be the ring of polynomials in x over f. F is a field. And f of x is equal to an x to the power of n a0 with an not equal to 0 and g of x be m xm b0 with bm not equal to 0 and m is greater than 0. Then there exist two polynomials q of x and r of x. This is called quotient, this is called remainder, such that f of x is equal to g of x times q of x plus r of x. We are not assuming the degree of f of x to be anything. If this is 0, then q of x will be 0 and r of x will be 0. And if it is less than this, definitely q of x is going to be 0 and r of x is going to be f of x. So we are just assuming that m is greater than 0. This is just like if you take f of x is equal to x cube plus 2x square minus x plus 1 and g of x equal to x square plus x plus 1, then if to find out the q of x and r of x, what we do is we'll do a long division like this: x cube plus 2x square minus x plus 1, x square plus x plus 1. So this will be x square, sorry, so x cube plus x square plus x minus 2x plus 1. This one is x square, so this will be plus 1. So x square plus x plus 1 minus 3x. So this is going to be our q of x and this is going to be our r of x. And that's what exactly this means. Here, one more thing we want to notice is where the degree of g of x, or probably we'll say degree of r of x, is strictly less than degree of g of x if f of x is different from 0. Okay? So that is a division algorithm. We are going to use this one to study the structure of an ideal in f of x. One more definition I want to recall is the irreducible polynomial. Irreducible polynomial over f of x. The definition goes like this: a polynomial p of x in f of x is irreducible if it cannot be expressed as a polynomial, expressed as a product of polynomials of degree less than the degree of p of x. That is, there exists no polynomials g of x and h of x such that p of x is equal to g of x times h of x, where degree of g of x is less than degree of p of x and degree of h of x is less than degree of p of x. This is equivalent to the prime number in the ring of integers. Irreducible polynomial. Now let us study some properties of the structure of an ideal in f of x. So let n be an ideal in f of x. So n can be a trivial ideal or a proper ideal. So there are three cases here. There are three cases for n. One is n equal to 0. The next one is n equal to f of x, the whole of f of x. And the third one is n is a proper ideal. That means this is neither a zero ideal or the whole of f of x. So the elements of n is coming from f of x. But f of x contains all the polynomials in x. And that includes the constant polynomials also. And 0. But if n contains a non-zero constant polynomial, non-zero constant polynomials means the non-zero elements from f. Then what happens? Then those elements are from those constant, non-zero constant polynomials are elements from f. Are elements from f. I'm going to write it here. Are elements from f. And that implies elements from f. F is a field. Elements from f means those elements have multiplicative inverse or they are units. That means those elements are units in f of x because they have multiplicative inverse. And if an ideal contains a unit, then that ideal is the whole of f of x. That means n is equal to f of x. So that is not possible. So the problem here is you are assuming that n contains non-zero constant polynomial. And you are arriving at a condition that if that is the case, n is equal to f of x. And our n is a proper ideal. So that implies n cannot contain non-zero constant polynomials. In other words, n contains only 0 and polynomials in X with degree greater than 0. With the degree greater than 0. Now we are going to apply the division algorithm. And before that, let g of x be a polynomial with minimal degrees. That means there is no other polynomial in n whose degree is less than this. And let f of x be any polynomial. In f of x. So we have two polynomials, g of x and f of x. G of x is the property of g of x is it is the polynomial which has got the lowest degree in n. And f of x is any other polynomial. Then you apply the division algorithm. Then using division algorithm, f of x algorithm, there exist two polynomials q of x and r of x such that f of x equal to g of x times q of x plus r of x with r of x, the degree of r of x with the degree of r of x strictly less than degree of g of x. Meaning g of x is a degree of the lowest degree in n. You say g of x is a polynomial with the lowest degree in n. So this is possible only if r of x is equal to 0. Because g of x is chosen in such a way that it is a polynomial in n that has got the lowest degree. So this implies f of x is equal to g of x times q of x. Because r of x is equal to 0. What does this mean? This means that f of x belongs to the principal ideal generated by g of x. How do you generate a principal ideal from g of x? Multiply every element of f of x by g of x, and this is an element from f of x. So f of x belongs to g of x. What does that mean? That means every ideal, every proper ideal, every proper ideal is principal. This is a principal ideal. This is a principal ideal. Principal ideal generated by g of x. that is when n is proper ideal. When it is not proper, this is also generated by a single element, and that is 0. And here it is generated by 1. Why it is 1? Because if you multiply every element of f of x with 1, it is equivalent to f of x. So, in either of these cases, any ideal is generated by a single element. In other words, every ideal in a ring of f of x is principal. So every ideal in f of x is principal. So we have the result like this. Every ideal in f of x is principal. Meaning it is generated by a single polynomial in f of x. Now our objective is to find out the condition on that generator so that this ideal can be a maximal. So we'll start from a maximal ideal. Let M be a maximal ideal in f of x. And this is an ideal, so you can always write it as M is equal to P of x. And let P of x can be factorized like G of x times H of x. M is a maximal ideal. M is maximal implies M is prime. Why? Because f of x is a commutative ring with unity. And P of x belongs to M because M is generated by P of x. So P of x belongs to M. That implies G of x times H of x belongs to M. And M is a prime ideal. That implies G of x belongs to M or H of x belongs to M. And M is generated by P of x. That implies G of x is equal to P of x times Q1 of x or H of x is equal to G of x or P of x P of x times Q2 of x for some Q1 of x comma Q2 of x in f of x. We already know that P of x is G of x times H of x. So this is not possible. This is not possible because we already assumed that P of x is equal to G of x times. That means if M is a maximal ideal, then we cannot factorize the generator, meaning this has to be an irreducible polynomial. So if, or let's write it like this, M is equal to P of x is maximal in f of x implies P of x is irreducible. So we just now proved that M is equal to P of x, the principal ideal generated by is maximal implies P of x is irreducible. Now let us assume that, so if it is a maximal element, this has to be irreducible. Now we'll assume that this is irreducible and see what happens to the ideal generated by P of x. So let P of x is irreducible. Let us assume P of x is irreducible. And M is equal to P of x. Now let us assume, let N be a proper ideal properly containing M, and that is M is contained in N, that is contained in f of x. N is an ideal, it's an ideal. So it is generated by another polynomial. N is an ideal implies N is equal to g of x for some g of x in f of x. Now M is generated by P of x. So P of x belongs to M, and that is contained in N, and that is equal to g of x. So that means P of x is equal to g of x times h of x for some h of x in f of x, because that is how a principal ideal is generated. This is not possible. This is not possible because P of x is irreducible. So that means if P of x is irreducible, we cannot find an ideal properly containing M, meaning M is maximal. That means M is maximal. So if P of x is irreducible, M is maximal, and if M is maximal, P of x is irreducible. So the result is an ideal M is equal to P of x is maximal in f of x if and only if P of x is irreducible. Now we have two important results or important properties of an ideal in f of x. the first property is any ideal in f of x is principal. Second result is an ideal m equal to p of x is maximal if and only if p of x is irreducible. Now let us compare the results in the ring of integers. So here we are taking r is equal to z, 0, 1, 2, and we have minus 1. Here r is equal to f of x. In the ring of integers, any ideal in Z is of the form NC. We already noted this earlier. And what is NC? NC is nothing but the ideal, the principal ideal generated by N. So here any ideal is generated by an integer. So that means any ideal in Z is principal. See the same result here. Any ideal in f of x is principal. What is the second result here? An ideal in Z is maximal if and only if P is prime, or an ideal, sorry, we'll write it like an ideal PZ is maximal in Z if and only if P is prime. The equivalent result here is number 2, an ideal M is equal to P of x is maximal if and only if P of x is irreducible. Here it is prime, here it is irreducible. Prime means you cannot factorize in Z. That is the same result here. P of x is irreducible, f of x means P of x is not factorizable. So that is a comparison of the ideals in the ring of integers and in the ring of polynomials.